To topic B, we just did A, and this is the additional SL questions again. So, mass M of a liquid, specific heat capacity C, flows every second through a heater of power P. What is the difference in temperature between the liquid entering and leaving the heater? So what we have is power is equal to energy divided by time, and we can write this as Q, and Q is MC, is the difference in temperature between liquid entering and leaving the heater. Okay, Z delta T divided by our time, and it says every second, so T is equal to 1, and we can cancel that out. So liquid fission. Okay, so what we then have is our delta T is equal to P divided by MC, and so that should be our answer. Our answer is C. Okay, now we have a fixed mass of an ideal gas, has a volume V, a pressure P, and a temperature 30 degrees Celsius. Gas is compressed to a volume of V6. Its pressure increases to 12 P. What is the new temperature of the gas? Okay, so compressed. So we have P1 V1 over T1 equal to P2 V2 T2, right? So we're trying to find what is T2. And T2 is just P2 V2 C1 divided by P1 V1. So let's do that. Pressure increases to 12P, so we have 12P times volume is V over 6, and we have temperature is 30 degrees, which is 30 plus 273, 303. Did not need to calculate that. And we have P1. I'm going to leave this as 300 just for simplification, but that's what it is. And then P1 is V, V1 is V. So these cancel out. What we have is 2 times 303, which is equal to 606. So our answer is D. Think. Right? Oh, they put it in Celsius. Okay. So never mind. We did not need to convert this. Actually, we did. 303, right? 303, and this is in Kelvin. Now, minus 273, so that then our answer would be C, right? Degrees Celsius. Watch out for those. Degrees Celsius. Okay. Now we have C. Any other? We have B again, okay. So this is B. Let's see. Electric motor of efficiency 0.75 is connected to power supply. EMF power output is 120. What is the average current drawn from the power supply? So power is equal to, right, and power is equal to voltage times current. And now this would be power out. Now when you find power out, that is equal to, or 120 times 0.75. Right, so current would be 90. 120 times 0.75 is 190. Sorry, 90. 90 divided by voltage 20. Sorry. What we have here is our power. Oh, they've given us the power output. Sorry. Current drawn from the power supply. Okay. So this is power in. And what we need to do is find power in. So power in 0.75. So that would just be 120 divided by 0.75. And that is 160. Right? So now we have 160 is equal to IV, and V is 20. I is equal to 160 divided by 20. That is 8 amps. So our answer should be D. Now what we have is variable resistors connected in series to a cell with internal resistance R. The resistance of the variable resistor is increased. What happens to the power dissipated in the cell and to the terminal potential difference of the cell? Okay, so what we have is our formula. EMF is equal to IR plus R. We're talking about the power dissipated, so E is equal to V. This is the terminal potential difference plus IR. Now, if the variable resistor is increased, let's look at this. V is equal to IR. Sorry, let's reorganize. V is equal to EMF minus IR. If we increase our resistance increases, then our voltage decreases. Sorry, that means our current decreases. Our voltage is fixed, right? Our EMF is fixed. And so then if our current decreases, then we have our voltage decreases. Sorry, our voltage increases. Right, looking at this formula, if this decreases, our EMF is greater than this, and our voltage increases. And so we can say it's either A or B. Then EMF. That was fine. Okay. And then we have power dissipated in the cell. Power is equal to R V over R squared. And so if R increases, then P decreases. So our answer is A, right? Hopefully that made sense. And let's see if there's any more topic B's. Okay, we have a Sankey diagram and we have black body. Okay. Sankey diagrams, nuclear power station, so this could be E as well. Electrical power output of the power station is 1000 megawatts. What is the thermal power loss in the heat exchanger? That is here. Okay, so we have 1000 is 4 blocks and 1000. Okay, and we have 4 blocks here, right? 1, 2, 3, 4. So it should just be 1000 and our answer is B. Right, these are to scale. So 4 blocks, 4 blocks. Okay, that's pretty simple. And we have black body radiation. Power it emits from a unit surface area depends on the temperature only. It has an albedo of 1. It emits, that is already wrong, right? Albedo is equal to more light reflected, right? More reflected, which is not true, right? Black bodies absorb all radiation. Nothing is reflected. And so B is wrong. It emits monochromatic radiation whose wavelength depends on temperature only. It emits radiation of equal intensity at all wavelengths. Let's look at Wien's law. We have equals constant, right? And at this W max, you have a max intensity. And so it does emit radiation at all wavelengths, that is true, but not of equal intensity, right? Intensity is different with the wavelength, so this is wrong. Now we have A and C. It emits monochromatic radiation whose wavelength depends only on temperature. It's not monochromatic. So no, right? It does not, it's not monochromatic. We just discussed that it's a continuous spectrum, right, of different wavelengths. Continuous spectrum, which means a bunch of different wavelengths. And now we're only left with A, and the reason it is A is we have our formula, right? Emissivity is equal to power per unit area divided by our Stefan-Boltzmann constant times T to the 4, right? And so our power per unit area is only really dependent on our temperature, right? Because these are both constants. These are both constants. Emissivity is specific to a material, right? Material specific. And so our answer is A. Okay, that's it for topic B, SL questions. Hopefully this helped and you guys learned a bit more. Do drop a like and subscribe if you enjoyed this.